which means it has how many protons?
8.
8, exactly right. And how many neutrons?
8.
Yeah, Adam, do you have a question?
Yeah. So will we be doing this rather than like a Lewis dot diagram or anything like
Right.
that?
When I ask you to diagram an atom, it'll just be like this. And because it's not carrying a charge, how many electrons does it have?
8.
Also 8. So there would be 2 in the first shell. How many in the second? 6. Exactly right. Now because I'm a little bit OCD, I like to make my electrons symmetrical, but I'm not particular about that. If you have those 6 electrons kind of randomly distributed throughout that final orbit, that's totally fine, just as long as you have the right number of electrons in each orbit.
I'm sorry, this might be a dumb question, but what does not carrying a charge mean again?
Okay, I'm glad that you asked that. In fact, Sarai, that is a wonderful segue into the next topic we're going to talk about, which are ions and isotopes. So an ion is any atom that carries a charge. What that means is an atom is either going to have a positive or a negative charge, and these are important because it makes them incredibly biologically active. Generally speaking, carrying a charge is an unhappy state for an atom, and it wants to do something to negate that charge. So if an atom carries a positive charge, it's called a cation or cation, and if it carries a negative charge, it's called an anion or an anion. Now, the chemical formula for that would look something like this. Let's say we have a nitrogen atom, which we know has the atomic number of 7 and atomic mass of 14, but it carries a negative charge. Now that negative charge tells us something about the relative number of protons and electrons. If it carries a negative charge, does it have more protons or more electrons?
More electrons.
It has to have more electrons, right? Because electrons are negative. So it's increased its negative electrical charge. Okay. So let's diagram this anion, this nitrogen anion. So nitrogen has in its nucleus protons, what? 7. And neutrons it has
7.
also 7. Oh, close to 14. But remember, this is the atomic mass. So really what we want to do is subtract the number of protons from that. Cool? Okay, so it carries a negative charge, which means it has how many electrons? Close to 7. 8. Why does it have 8? Yeah, it's got one more negative charge than it has positive charges. Yeah, Adam.
It takes on and doesn't, right? If it was a cation, it would give away that electron.
Very good. And we'll do an example of that next. So, let's diagram this. If it has one more negative charge, it has one more electron. So how many of those electrons are going to go into the first shell? 2. Always 2. And how many are going to go to the second one?
8.
Close.
4. 8,
Closer.
6.
Again, we'll go for, okay, yeah, why 6?
Because it fills the whole thing. It will fill the whole.
So we started here with 2. It filled that whole one. And how many total electrons
Oh,
are
8.
there?
It needs
There are
8. Yeah.
And so if we take those 2 from 8, it's going to be left with 6, right? So it's going to have an electron there, 2 there, 1 there. Okay. So that's a negatively charged nitrogen atom. All right. So let's consider, yeah.
So you said that the other had just one minus its negative. It's just you take just one.
Yes.
You add one more
I like where you're
electron.
going with this.
So how do you know if it has more
Oh,
or?
that was a wonderful question. Carries 2 negative charges, it's 2 more electrons.
Just two more?
So
Yeah,
you just
then-
add another one, so instead of being 8, it'd be 9.
Exactly right. And where would we put that 9th electron?
In there.
In this shell, right? In the second shell, because this can accommodate up to how many?
8.
It can accommodate up to 8. And it only has 6, so it can take another one. Yeah, Adam.
In that diagram, does it matter if that dot you just put on goes on the bottom or the top?
Yeah, no, I don't really care. Just so long as you have the right number of electrons. What if it carried, yeah, go
I
ahead.
just want to make sure I got this right. So
Okay.
electrons are the number of the negative charges.
Correct.
Okay.
Yeah. And the starting point is always atomic number, right? If this didn't carry a charge, there would be 7 electrons. But it's going to be 7 plus 1, 2, so a total of 9 electrons.
Thank you.
Yeah,
So
go ahead.
I have a question about the shells.
Okay,
So when do we know we need to use more shells?
good question. So remember, the first shell only accommodates 2,
Mm-hmm.
and that's always and forever. So if an atom has just a single electron, right? It's going to have just a single electron in that first shell. It can accommodate up to 2. So as soon as we hit 3 electrons, we have to go out to the next shell. So electron shell 1, and I'm just going to abbreviate that ES. Electron shell 1 can only accommodate 2 electrons. Electron shell 2 can accommodate 8 electrons. Electron shell 3 can also accommodate 8 electrons. So an atom with 3 electron shells can accommodate how many electrons total? Yes, very good, because it's 8 plus 8, 16 plus 2. So it can accommodate up to 18 electrons. Okay? Before you go to the second energy shell, though, or electron shell, you have to fill those 2. So as soon as you hit 3, you bump out to the second one. As soon as you hit 10, you bump out to the third one. You okay with that idea? Okay, let's do a cation. So I'm going to give you a new element, and we're going to call it sodium. So sodium, which has the atomic symbol of Na, has the atomic number of 11. It has the atomic mass of 23. And we're going to say that sodium carries a positive charge. Okay? So, in the nucleus, how many protons are there? 11. Exactly right. How many neutrons are there?
12.
12. How many electrons are there?
10.
Why 10?
Because you take away from the neutrons to make it more positive, or to make it equally positive.
Exactly right. You subtract an electron to make it more positive. Why couldn't we just take a proton away?
Because then that would make it a negative, because then you would have less protons than neutrons, and neutrons are negative.
Why couldn't we add a proton? Doesn't that seem simpler? I mean, if it's more positive, just stick a proton into it.
That would change the atomic number.
Yeah, and it would no longer be sodium, right? If you add another proton onto it, all of a sudden it becomes magnesium. It's no longer sodium. You guys, when you're mucking around with charges, only change electrons. Don't change protons. Okay? That's a really common mistake. So I really like to ask you guys to diagram ions, because it requires that you understand how to diagram an atom and really what's going on to make an ion, okay? And when you're making ions, just muck with the electrons, don't muck with the protons. Okay, So how many electrons are going to go into that first energy shell? Of the 10 that we have,
2.
2. Very good. Which leaves how many?
8.
8.
Which fills this.
And all of those are going to go into the second one, right? Because it can accommodate up to 8. So, as a bit of, I guess, a preview for our discussion in a few minutes, this is a really happy state for most atoms, to have all of their energy shells filled. That's what they're going for, okay? All right, are there questions about ions? Okay, so in addition to asking you to diagram an atom or an ion, I could ask you something like, which of the following is defined as a positively charged atom? And give you cation, anion, ion in general, or element. And the correct answer would be cation. Very good. Ion would also be correct, right? But it's not as correct as cation is. Now there's another variant of an atom, and that's called an isotope. Isotopes are cool because we actually use them quite frequently in medicine. So an isotope is any atom that varies with respect to its neutrons. A really, really common isotope is carbon-14. Now, I would be a little bit surprised if nobody in here has heard of a process called carbon dating. So carbon dating is a way for us to use naturally occurring isotopes to measure how old some dead organism is. Okay? So an isotope is any element that varies with the number of neutrons. So carbon isotopes. We know that carbon has an atomic number of 6 and an atomic mass of 12. An isotope is changing the number of neutrons. So what that means is, one isotope of carbon is atomic number 6, atomic mass 13. How have we made carbon 13 from carbon 12? What did we add to it? One neutron, right, which makes it an isotope. Yeah, very good. And then we also have carbon 14, which means that we've added 2 neutrons, right, to carbon 12, or a single neutron to carbon 13. Now, both of those isotopes, carbon 13 and carbon 14, are unstable, and they're naturally going to want to degrade. Nuclear degradation is called radioactivity. So when the nucleus of an atom starts to fall apart, that's radiation, and that's nuclear decay. So nuclear bombs, for example, start a chain reaction in which nuclear decay goes rampant. We split an atom, it causes charged particles to shoot off, start interacting with other atoms, which causes their nuclei to fall apart, and it just causes all sorts of problems. The cool thing is, though, we can use controlled, safe isotopes in medicine. There's something called a PET scan, and a PET scan is commonly used to identify cancerous tumors, which is redundant because any tumor is a cancer, but particularly malignant tumors, those that are really, really bad. So what happens with tumors is they become, at a cellular level, incredibly active. They begin dividing outside our body's normal control. And nuclear divisions and cellular divisions release a lot of electrons. It requires a lot of energy. What PET scans do is they inject an isotope that interacts with free electrons, and it begins to glow. So this is what a PET scan would look like, of like a thyroid gland. So what we can see is there's some glowing regions here and here. That's where some radioactive isotope is interacting with some free electrons. And what that does is it allows us to pinpoint where it is tumors are inside our bodies. We can also use it for dating organic material. Now, carbon-14 dating has some pretty significant limits. There actually has to be some organic material for us to date. So if you guys watched like the original Jurassic Park, they refer to carbon dating of fossils. You can't do that because most of the time a fossil is just a mineralized deposit. What happens with fossilization is some organism dies and then all of its fleshy material and all of its bones are replaced with minerals. And so a fossil really is just a rock. It doesn't have any organic material, no carbon really left. But if you were to go to like the ice fields of Siberia and you were to dig up a mammoth or a mastodon, you could take the fleshy parts of the mastodon and measure the relative abundance of carbon-14 and carbon-12, and you could estimate how old that organism is, or at least how long it's been dead. So how does that work? Well, with carbon dating, what happens is all of our bodies maintain some natural ratio between carbon-14 and carbon-12. Carbon-14 is a radioactive isotope that doesn't hurt us. Plants pick it up from carbon dioxide that gets affected by solar radiation. And then we eat plants and we pick up that carbon-14, or we eat organisms that have eaten plants and we pick up that carbon-14. And our bodies maintain a constant ratio between carbon-14 and carbon-12. When an organism dies, however, that carbon-14 begins to degrade into nitrogen-14. So one of the protons in carbon-14, one of the neutrons in carbon-14 gets replaced with a proton. So we shift from carbon-14, which has C6, C14 to, N7, 14. So one of those neutrons is converted or replaced by a proton, and it becomes this. So our bodies never lose carbon-12 concentrations, but the carbon-14 concentrations begin to degrade as soon as we die. And so you can take any organic material, measure that ratio between carbon-14 and carbon-12, and pinpoint when that organism died. Now the way that we do that is something called half-life. Half-life is a measure of how long it takes the total amount of some radioactive isotope